Suppose this is a nuclear reactor located at, say, Germany. An explosion occurs. The nuclear reactor explodes, spilling highly hazardous radioactive waste around the area. A robot is now sent to perform a search and rescue operation in areas that are deemed hazardous. We need the robot to visit each designated key location and alert the headquarters if a casualty is located. However, the commander of the search and rescue task force wants the robot to visit each location only once and then return to the start point. The robot should also find the shortest such route due to the urgency of the situation. For example, for 5 locations, there are a large number of ways in which the robot can traverse each location once and return to the start point. To solve this problem, we first break the problem up in steps and try to represent the problem using what is known in maths as graph theory. First, for each location, we know that there's a fixed distance between that location and some other location. In terms of graph theory, we can represent each location to be a vertex on what is known as a graph. The line joining each vertex is then known as an edge. The distance in between 2 locations can then be represented as weights in the graph. The graph is now known as a weighted graph. Now that we have represented our problem on paper, we can then begin to solve it. In fact, it so happens that the possible solutions to our problem is also what is known as a Hamilton circuit. That is, a graph cycle through a graph that visits each node or vertex exactly once. The Hamilton cycle is named after Sir William Rowan Hamilton, who devised a puzzle in which such a path along the polyhedron edges of an dodecahedron was sought.
Let us now move on to the most obvious way of finding the shortest such circuit on a graph. The most intuitive method is, of course, to find every possible Hamilton cycle, compare their total distances or weights, and the path with the shortest distance would inevitably be the solution. To do this on a graph of low order, meaning a small number of vertices, is in fact trivial and easy to do. For a graph of order 5, we have only 24 possible paths. For a graph of order 6, we see 120 possible paths. For a graph of order 10, however, we begin to notice that we start to have considerably more possible Hamilton circuits, already over 362,000. We realize that the number of circuits the algorithm has to consider increases exponentially with the number of vertices in the graph. If we had 50 locations the robot had to visit, it would amount to 49 factorial possible circuits, and thus to find the shortest one, the robot will have to compute all 608 November decillion paths, that is 6.08 times 10 to the power of 62 paths, and find the shortest one. It would thus definitely not be feasible nor reasonable for us to do such a computation on the robot. In fact, it would take even a supercomputer ages to do such a calculation. We thus classify this method of solving the problem as computationally inefficient, as the time taken for it to run increases exponentially compared to the problem. This kind of straightforward method, or more precisely, algorithm, is known as the brute force algorithm. If ran to completion, it guarantees the optimum solution, but it would take a very long time for it to do so if the problem set is large. In fact, for this particular problem, there is no known efficient algorithm that will give us the shortest Hamilton circuit in a reasonable amount of time. To have our robot continue its mission, we therefore have to compromise. What we can do instead is to settle for an approximation algorithm which will give us a fairly good answer to the solution in what we call polynomial time. Polynomial time just means that the time taken to solve the problem increases as a polynomial. For example, quadratically with the size of the problem instead of exponentially like before. In other words, the required time for finding a solution grows gradually with the number of locations. Therefore, we sacrifice getting the most accurate solution, or in this case, the absolute shortest path, for a path with distance quite close to the shortest, and acquiring it in a reasonable amount of time instead. Let us now look at one such possible algorithm, commonly known as the nearest neighbor algorithm. Its concept is pretty simple. Basically, it has us picking any location as our starting point and choosing the next location based on the shortest distance between them. We continue doing this for each node, tracing our path as we go along until we have visited all locations. But we must do it under the condition that we do not choose locations we have already visited. We then trace a path back to the starting point, and the resulting loop is our solution for hopefully an optimally or near optimal short Hamilton circuit. Intuitively, we can already see that this method assumes that every location is accessible from every other location, or else we will get stuck at some point and the algorithm would not work. In graph theory, we would say that a graph is a complete graph. In formal terms, the algorithm is as follows. First, we start by picking any vertex as the starting node. Next, choose the next node as the vertex for which its corresponding edge has the smallest weight. Continue building the circuit by repeating the above steps under the following conditions. We do not visit a vertex that has already been visited. We do not close the circuit until the last vertex has been visited. From the last vertex, return to the start node to close the circuit. We then add up all the weights to look at our result. By repeating the above steps for each of the n vertices, we can obtain n results. We compare these n results and use the shortest route. This is the repetitive nearest neighbor algorithm. When we have a large number of vertices, the brute force algorithm is not realistic as we have seen. However, with the nearest neighbor algorithm, if we have 10 vertices, we just need to do 10 calculations. And with the repetitive nearest algorithm, we need to find n number of ways and use the best one. This is not the most efficient route, but it is a good approximation and much less work is needed. Now let us look at another possible algorithm, the cheapest link algorithm. This algorithm works as follows. Firstly, we rank the weighted edges of the graph in ascending order as follows. Then, we select the smallest weighted edge, meaning the cheapest link between the two vertices. After doing that, we select the edge with the next smallest weight. For our subsequent choices, we have to consider two conditions before making a selection. The first condition is whether the edge selected forms a closed circuit with the preceding ones. Second condition is whether it causes a vertex to have 3 selected edges. If either one of the two conditions are true, we do not select the edge. We then consider the edge with the next smallest weight. We repeat the steps until we obtain the 2 edges for each vertex. This will form a Hamiltonian circuit. No matter which vertex we use as starting point, we will pass through the circuit with the same total weight. Now, let us take a look at an illustrated example. We consider a problem with 5 vertices, with vertex A, B, C, D, and E. The weighted edges of the graph are as follows. Now, we list down the edges from the lowest to the highest. We have 120, 127, 129, 139, 141, 143, 177, 178, 192, and 200. Next, we are going to draw the Hamilton circuit. As the algorithm says, we are to pick the first 2 smallest weighted edge first. So, we use 120 and 127. We highlight the path. Next, we take a look at 129. If we pick this weighted edge 129, we will be contradicting the second condition. This is not causing a vertex to have 3 selected edges. Thus, we skip the weighted edge 129 and we look at the next weight. Let us look at 139. If we pick the weighted edge 139, we are going to close the circuit with the preceding ones. This contradicts the first condition. So what about 141? If we pick 141, it wouldn't cause the preceding edges to form a closed circuit, nor will it cause a single vertex to have 3 selected edges. So we highlight the weighted edge 141. So can we use 143? Well, it looks pretty clustered now. Do we close the circuit if we use 143? It may seem confusing, but if we look carefully and trace the path, it doesn't close the circuit. So, we can pick the weighted edge 143. Now it seems pretty clear which is the remaining edge. But we shall not highlight it yet. We will go through the rest of the weighted edges one by one. Let's look at 177. Well, it causes a vertex to have 3 edges, so we neglect this weighted edge. 178 also causes a vertex to have 3 edges, so we also neglect this edge. 199 also have this problem, and we eventually end up with the final edge 200. We highlight this edge now. So as you can see, what we have in front of us is a Hamilton circuit. If we add the edges up, 120 plus 127 plus 141 plus 143 plus 200, it gives us a total weight of 731. And the Hamilton circuit is A, C, E, B, D, A. There are certain assumptions that we made throughout this entire course of the presentation. Firstly, there need to exist a Hamilton cycle for the n locations. We also assume that the distance between each of the n locations is known beforehand. Next, we assume that either there are no obstacles or the robot is able to detect them and overcome them. If there are obstacles, it should not affect the known distances. Finally, each of the n locations must be connected to every other location.
This was a triumph. I'm making a note here huge success. It's hard to overstate my satisfaction. Aperture science. We do what we must because we can. For the good of all of us, except the ones who are dead. But there's no sense crying over every mistake. You just keep on trying till you run out of cake. And the science gets done and you make a neat gun for the people who are still alive. I'm not even angry. I'm being so sincere right now. Even though you broke my heart and killed me and tore me to pieces and threw every piece into a fire. As they burned, it hurt because I was so happy for you. Now these points of data make a beautiful line, and we're out of data, we're releasing on time. So I'm glad I got burned. Think of all the things we learned for the people who are still alive. Go ahead and leave me. I think I prefer to stay inside. Maybe you'll find someone else to help you. Maybe Black Mesa. That was a joke, haha, that chance. Anyway, this cake is great. It's so delicious and moist. Look at me still talking when